So we're going to use the Leibniz form of the chain rule, which is essentially still derivative. So I guess I should write that in here. Of derivatives of chain. Leibniz form of derivatives of chain rule. A little too many ofs, but that's essentially the idea here. So we're going to use the Leibniz form for derivatives of a chain rule. So what does that look like? Well, here is essentially the notation for it. If y is equal to f at u and u is equal to g at x, so essentially a function within a function, and they're both differentiable equations, then the derivative of dy dx is equal to dy du times du dx. So this multiplication is going to come in a little handy here. So what does that mean to us? Well, that means is we're going to derive a function of y in reference to u. So that's this first one here. So we're essentially just going to derive this function. You could write it as, we don't tend to write it, since it's not Lagrange style, we're doing Leibniz, we would actually write dy over du is equal to, this is the same idea as y prime here. And we just derive this. Well, I bring down that coefficient, it becomes negative 3 u to the power of negative 4. Okay, that's great. And then I then derive the second part. So actually, I'm going to highlight these things so we know what we're doing here. This was dy du, so that was this part here we just derived. Next, what we're going to do is we're going to derive u in reference to x, and that's this equation here. We have the u and the x. So we derive this function. This becomes 2 minus 3x squared, and that is essentially this half of the equation. So du dx, which is that. So what does it tell us to do? Well, it tells us to then multiply these two equations together. Great. So I can then, so in order to find dy over dx, I multiply the two. So I'll set them in sets of brackets. Negative 3 u to the power of negative 4 times 2 minus 3x squared. I'm going to make this so it's a positive exponent. So it's 1 over negative 3 u to the power of 4 times 2 minus 3x squared. Now think of this like multiplying fractions. We do the top by the top, bottom by the bottom. So this will become, this will essentially become the numerator, and this will become the denominator.
Minus 3 is on top. And then the u goes down.
Yes, you're right. 100% right. Thank you. That would have had to have been like this for this idea to have happened.
I got that wrong in the test.
Ah, very good memory. So the 1 on top, think of it like 1 times negative 3, so the negative 3 stays on top. So actually, for the multiplying of these fractions, I hope this is clear now. Ooh. This is actually becomes like a distributive property. So it's still going to be u4 on the bottom. Okay. We're going to distribute this negative 3. So negative 3 times 2 is negative 6. Negative 3 times negative 3x squared is positive 9x squared. You could say, okay, great, I'm done, but we're not, because this is differential of y and x, but we have a u in here, so we have to replace u. Well, what is u originally equal to? It's originally equal to this, 2x minus 3x, or sorry, x cubed. So the numerator stays as negative 6 plus 9x squared divided by, I've already forgotten, is it 2 minus 3x squared?
Yeah, 2 minus x cubed.
2x minus x cubed, that's it. Minus x cubed. But all of this is to the power of 4, yeah. So think of it like we replaced u with this part here. So that's to the power of 4. I mean, we could have expanded this and get a very, very large number at the bottom, but I think this is mostly what they're looking for. We could common factor the top out here. You could take out 3 from each of those, so you get, yeah, and we could take out negative 3 or positive 3. It doesn't really matter, because I could change the order of this. So if I take out positive 3, it'd be 3, this would be 3x squared minus 2. Might be a little easier to look at that way, over 2x minus x cubed power 4. And then, like, I could expand the bottom, but this is a nice simplified version. It's essentially a factored version of this. And that would be it for this notation.